that we are having. We have the full editorial access to change any particular points, to change the methods that we are using, to change the iteration points, to change the k point sampling, which I will be further explaining while giving out the live demonstration of the tool. Furthermore, apart from this, we have also various different implemented methods. So to showcase how it is effective for both new users and experienced users, for new users, it has a very dedicated GUI, that is graphical user interface, in which any new user, if needs to learn about a tool, so it can learn very easily. We have a tutorial guide that has interactive tutorials, so we can see the GIF controls. We already have the Python files, which if some user is familiar with the Python scripts can directly be run and simulated. Apart from this, there is one more inclusion in the latest version, that is GPU accelerated simulations. So earlier on, DFT-based simulation used to take too much amount of time to do the particular sets of simulation. Now, what we have is we have the particular GPU accelerated simulation, wherein what we can do is whichever model that we are creating out, we can have the GPU accelerated simulation, and if we need to process it faster, so we can reduce out the particular sorry. So what we have is we have the particular GPU accelerated simulation, in which whichever simulation that we used to run, for example, 2 days, 3 days, 5 days, or even 16 days, 17 days, has now been reduced down to probably hours or couple of days, depending on the particular size of the structure that we are having. And once we are using the particular GPU accelerated simulations, what we are further doing is we are doing the multi-parallel executions of the process on different number of cores inside the GPU. So this way, larger structures can be implemented. We can do the particular transport calculations, even to do the particular magnetic and anisotropic energy or any other magnetic properties calculation that can be done in a very easy way. Apart from that, we have a seamless integration with the TCAD level. So whatever material that we are developing at quantum ATK software, we can furthermore take it all the way to TCAD and carry out and do all the sets of simulation that is required, like the particular electrical behavior, the thermal behavior of the devices that we are having. And furthermore, if we are working on a particular integrated circuit chips, so IC chips can be fabricated and we can do the particular import of whatever properties that have parameters that have been calculated in quantum ATK, which were later on carried on to TCAD software, and ultimately to the particular IC chip that is front-end and back-end solutions that we are having in Synopsys. So we have a seamless flow for that. Now, moving up to the next slide. At what level we can develop the particular sets of devices? So we start up with the molecular level. So any molecular level devices can be created out right from starting a single atom. So even we can create a particular structure comprising of a single atom. Now, if we are having multiple surfaces, we need to do the surface process simulations. We need to do the calculation of properties like adsorption, absorption. That can be done using the different surface tools that we are having. Then if we need to create interfaces between two different materials, or if we need to create junctions. For example, if we are creating a gold, benzene gold device, that is a molecular device that we need to create it. So that can be done using the interfaces builder. Then whatever structure that we are creating them, we can directly convert it into devices. We have a devices inbuilt tool in which any bulk structure that we are having can be furthermore converted into devices. We can set out the different regions present in it and then develop it accordingly. Coming on to the next part is the complex material creation. So once we are talking up at the nano level, so we need to have certain tools that help us in building the following structures. In quantum ATK, we are supported with multiple levels of operations. So right up starting with a particular nanoparticle builder, so we can basically set out the particular radius, we need to set out the particular element for which the nanoparticle needs to be built up, and we can create an entire structure directly while setting up input in the GUI. Apart from that, we have certain nanotubes builder like to develop graphene nanotubes, as graphene is one such material that is being used in majority all the particular devices that are being used at miniature level because it has very good properties, right, for conducting as well as insulating. So since it caters both the properties, it's one such device that is being used. So apart from this, any complex material that needs to be developed in can be directly worked on in quantum mechanics software. Then what we have is we have the polymer equilibrization block. So if we are having one set of monomer or multiple set of monomers, if we need to basically combine different sets of monomer to build a polymer, that too can be conducted and we can directly build up the entire structure for. And last but not the least is nanostructure building. So since it was already explained in the complex materials, we have certain plugins in which we can directly build out entire structures. Apart from that, we have the particular amorphous pre-builder in which any complex material can be built in. Just we need to write in the chemical formula of that material and multiply with the number of size of the structure that we are having. Apart from that, if we are having a lattice of any particular surface that we need to basically model it at a larger scale. So what we can do is we can just set in the particular lattice structure formula. We can see we can set in the value of ABC, alpha, beta, gamma values, and whatever type that we are creating, we can create an entire device out of that. Now, coming on to the next slide, since the particular system configurations are already explained, what sorts of materials can be created to go through the particular process or the particular what we say workflow. It's very simple workflow that we are having in quantum mechanics software. Starting up with the building tools. So we have basic building tools. We have a 3D builder in which any particular structure can be built in. We can do all the sorts of modifications. And to start up with any complex structure, we can develop out even any functional materials that need to be developed in that can be used in using the building tools. Then we have the databases. So we are having two type of databases in quantum ATK. The first one being the internal database library that comprises of the certain structures that are already present, like bulk structures, the molecular structures that we can directly use and build it accordingly. Apart from that, we have internet-based library. So there are multiple libraries that are available on web, which can be accessed in, and the materials can be directly imported from that particular file. That can either be PubChem database, that can either be crystallography open database, or even the materials project. So we just need to type in the particular, select in the number of elements that we are requiring. For example, if we type in hydrogen and fluorine, and if we just select out the element type HNCl, so it will give me all the permutation and combination of all the particular structures that are available over the web, and we can directly import it in. So this comprises the particular builder part and the database part. Once this step is completed, we move on to the particular next step. That is to set up the particular calculation that we are basically requiring. So to do that, what we have is we have different sets of calculators as I explained earlier. Depending on our requirements, we choose the different sets of calculator. For example, if we are having a particular atomic structure less than 10 atoms, so we can use a plane wave, which will give the highest accuracy, but the computation time would be also significantly higher. If we have a larger structure, for example, if we are particularly working on atoms around 100 atoms, so in that 100 to 1000 atoms, so in that case, a DFT LCO based approach can be used in. Then comes in the next part. If the particular structure is much more larger, around 1000 to 10,000 or probably 50,000. So in that case, semi-empirical calculators can be used. Then once the particular structure size increases more than lakh, so these all the calculators that I mentioned earlier are of no use. Because even if we are doing the simulation, it won't be very efficient for us. It may take a couple of months to complete out the following simulation using the older approach. So what we have is we have the particular existing force field based approach in which either we can use the existing classical force field or we can also use the machine learned force field. So we can develop out different sets of molecular dynamic simulations to develop out certain materials. We can have MTP generations, that is moment tensor potential generation. And once the particular files have been created, we can furthermore develop out the structure. This comes in the calculation part. We set up our calculator, that is the simulation engines that are being required. And once the particular simulation engines are set up, what we set is which property we need to calculate. So for example, if we are starting with a band structure, so we can select out a band structure and we can start up doing the particular simulation. Another case, if we are requiring, for example, Raman spectrum, so that can be selected out and the simulation can be started. Once this set is completed, we have loaded a particular material either from database or we have created a particular material. Then we have set up a calculator. Next up, we have set up the property that we need to calculate. we have MTI parallelization in quantum. So what we can do is we can simulate the particular simulation job over 256 different cores simultaneously. So we can fire up the job and it can run on multiple cores so that we have a faster result generation. It's not just limited to 256 cores. If we have a limited device about 8 cores, so we can still do the simulation, but the simulation time would increase accordingly. Once the particular job has been created and we have run the simulation, we have got our desired results. So we have certain analytical tools to analyze the particular studies. So for example, if we have generated out the IV studies, so it will be giving us multiple points like transmission spectrum, thermal current, and many more. Whichever point we need to select, we can highlight that, we can convert it out into any sort of CSV report or a text report. And even if we need to do the particular sets of visualization, so for example, a molecular dynamic simulation may require a visualization, or an energy elastic band may also require a visualization. So that can be done using the visualization tools that we are having. Last but not the least is the Python scripting that is very much helpful for because even certain properties that are missing in the GUI itself, we can cover out that in using the Python scripting method. So any pro user of quantum ATK can edit up the particular script. It's a very easy to editable script that we are having because we have all the particular points, we have corresponding lines that are mentioned that can be used at any point. So this way, particular structures can be created out. Now, in coming back to the particular DFT simulations, so earlier on I mentioned that we have two sets of methods. One is plane wave basis set and another one is the LCAO basis set. It is linear combination of atomic orbitals basis set. In the plane wave basis set, if we have limited sets of structure around 10 atoms or less, we can use a plane wave basis set. It would work. Even around 50 atoms, it may work. But if the atomic size increases, the particular solution time would increase omega big of n cube log n to that. So if we have two number of items, so it fit around 8 log 8, 8 log 8. So it's significantly higher the simulation time. Whereas when we are considering our LCO based approach, so the particular job length increases linearly. So as the number of items increases, so is the particular computation time that we are having. Why so? Because there is a one common reason that when we are considering a plane wave basis set, so it will also encompass the particular vacuum spacing that is present in the entire structure. What we mean by a particular vacuum spacing that I will further explain during the live demonstration part. But coming back to the particular LCU basis set, since it basically neglects the particular vacuum spacing, so we can just ignore the following part and the simulation is much more faster. Now coming on to the particular device simulations that we have in quantum ATK at a nano level. So what we have is we have a TFT plus NEGF based method to basically simulate out different properties. We can develop out any sort of devices like solar cell application if we need to do, if we need to calculate the photon currents, the photocurrents, then if we are doing an IV characteristics calculation, then bias and gate to simulate various resistance, capacitance, all the particular things can be simulated in. And even the larger structures around 10,000, 10 to 1,000 to 10,000 can be simulated using a semi-empirical based approach. So this is another option that we have in quantum ATK for device simulations. Then these are the key material and modeling areas. So semiconductor is one such industries that is heavily relying on for the development of chips at a nano level. Then we have the batteries that require various sets of new sets of complex materials. To design batteries that may be long lasting and may be biodegradable in the environment. So it causes lesser harmful effects in the environment. So that's one such case. Then to develop new sets of solar and fuel cells so that in a minimal area, the maximum energy efficiency can be produced in. Then to design different sets of polymers, it can be used to do the particular catalysis simulations. It can be used, and even developing different sets of metal interconnects, ceramics, and glasses. The software can be relied on. Then this is already been explained the particular workflow that we have. We have the build, wherein we will be building the particular structure, then selecting out the calculator, simulating the properties, and ultimately analyzing the particular sets of results. So one such important part is why do we need particular force fields? So whenever we will be dealing with structures that are related to industries, so it won't be in some of number of items around 100,000. It would be basically more than 10,000 or even will cross more than lakhs. So what we need to have is we need to have a particular set of approach in which we can simulate larger structures in a lesser computation time. So what we will be doing is even if we need to do a complex structure generation, so the force field can be used in. If we need to do the particular mechanical properties calculation to do the stresses, forces analysis, it can be done. Thermal properties analysis can be done. Electron phonon scattering can be calculated in, then any sort of diffusion process, any defect generation, if present or if we need to create in, can be generated, and even the process simulation. So what it does is it increases our quality of result in a less turnaround time. So ultimately, our efficiency increases in four folds. Then we have a particular mapping of the same, how the particular accuracy is proportional to the computational cost. So when we are dealing up with a particular classical force field, so we will be having the least accuracy, but the computation time, that is the particular simulation time, would be also quite less. When the particular size of structure increases, we have used the semi-empirical based approach, either extended huckle or Slater coaster. We will be having higher accuracy as compared to the classical force field, and but the computation time would also increase. Then we have ab initio based DFT simulation, that is DFT LCO and DFT plane wave. So what it would be giving is it would be giving us the highest accurate results, but the simulation time would be quite high. So it may take around a couple of hours or days to do the simulation. We have one such example of amorphous HF42 hafnia that comprises of 96 atoms. So molecular dynamics simulation was conducted in, and using a particular DFT based molecular dynamics simulation, it took around 3 hours 20 minutes to complete out the entire process. But when we relied on the machine learned force field, so it gave us accuracy somewhere between semi-empirical and ab initio at the time almost similar to the classical force field. So the classical force fields, sorry, the classical force field took around 9 seconds, and the machine learning based approach took around 10 seconds. But we got much more higher results at a lower computational cost. So this is one such field that has been developed and that is being used widely in the current industry requirement, specifically for the nanomaterial design. Then this is how the particular GUI looks like. So we have a complete workflow for the same. We have the project section in which we can set out different number of users that we are having. Then we have the data view section. Sorry, just a second. Yeah, sorry. So what I was saying is we have a particular project section in which a number of users can create their different sets of project folders, and each and individual user can work on their project separately. Then we have the data view section. So whatever simulation that we would be conducting would get recorded in the data view section that can be accessed at any time. So any sort of optical device simulation that we are doing, even if we need to view the structure that we have developed in, that can be checked in. So any sort of data on the analysis that we need to do, we need to access the data view folder. Then we have the particular builder section in which we can build the structure entirely from a single atom to all the way to the supported builder tools that we are having in the builder panel. This would be better explained in the live demonstration. So I think I can skip this particular part. Then these are the particular advanced analytical properties that we can calculate. So we have the particular molecular dynamic simulation. Even the most important part being the particular optimized geometry. Since whatever structure that we are creating, if it's an unknown structure, we may not know what should be the exact lattice or what should be the exact spacing between the atoms. So what we have is we have the optimized geometry block. So software will automatically select out the structure that has least stress and least strain, so that the quality of results are quite high. So we can use anytime the optimized geometry, and basically it is preferred every time to optimize geometry of any block that we are basically working on. Then we have a dynamical metric, so we have a number of case and point samplings in which we can increase the particular dynamical metrics. So higher the particular k point sampling would be mean higher accuracy, but it will also increase the simulation time. Then we have the charge point defect calculation. Then we have AKMC, that is adaptive kinetic Monte Carlo simulations. We also have time stamp force biased Monte Carlo simulations. Then we have ME using our vampire scripting. We have polymer regularization, so any heterogeneous polymer can also be done. So there are multiple advanced analytical properties that can be simulated. Then apart from, we have basically three blocks. We have advanced analysis, we have computable characteristics, and we have the studies block. So either way, all the particular templates can be used, can be worked on, and the properties can be calculated. So you can see there are multiple computable characteristics, right from bend structures, current density, density of states, then eigenvalue, electrostatic potential, fed band structure, forces, and many more. So there are multiple characteristics that we can furthermore simulate. Then these are current user base that are working on quantum ATK in India. I'll be just starting up with the live demonstration. And after the live demonstration of quantum ATK, maybe of around 20 minutes, I'll start up with the brief introduction about simple web and how we are basically using the following tool. So let me just stop sharing the screen on this particular device. Yeah, so I hope my screen is visible in this whole device. Now, to start up with quantum ETK, as explained in the presentation itself, this is the project section. So we can create n number of users within it, and we can start up with the following set of solution that we need to calculate it. Then what we have is, we have the data view section. So in the data view section, we can see out any results that we are having and we are trying to simulate. So whatever simulations have been performed in earlier, we can anytime access the result. We can obtain the particular following graphs, we can manipulate different sets of settings that are being present. And this way, any result that has been submitted can be visualized in the data view section. Then we have the first building block. And whenever we are dealing with functional materials or the advanced complex materials, this is the starting block that we have to develop up with the following material. Either we can start up with a new configuration. So we will be getting a single hydrogen atom that can be later on changed with any element that we need to select from the periodic table. That too, we have the following isotopes of the particular element that can be selected in, and anytime the structure can be built. So I'll just show a quick guide to develop out the structure. So this way we can develop out multiple structure. And once the particular structure has been optimized, then it will automatically calculate the bond and it will automatically create out the following bonds for the following structure. A better way is always to either use a crystal builder wherein we choose a particular set of lattice and then we select out the particular ABC, alpha, beta, gamma values, and then selecting the element and its size. So this way we can easily select out multiple elements. And if we are having multiple surface different, so I can just select over here, then setting up the particular dimensions we can do is we can select out 0.5, 5, and now we can easily create any sort of structure. We can change the element from here. So this is just a preview. So how we can basically manipulate out different sets of structure to be building in, like starting from the space group, we have multiple sub-space groups that can be selected in. Then the type of cell size that we require, primitive or conventional. So this is one such approach. A better approach is always to either use a plugin. So we have a crystallography open database. To open that, we need to go over here and we need to select out the elements that we are submitting. Certain times the particular dataset library server is down. So in that way, what we can do is we can directly go and search in the COD identifier number. And once the particular element has been selected in the structure that we need to work on, we can directly bring that in our particular view section and then modify it. So in this particular case, the particular SQL server of the structure is not working. So what we have is whenever you will be searching on open web, the crystallography open database, so the structure has a COD identifier number that can be anytime brought in and we can type in directly over here. So we can open the site from here, and once the site has been opened, we can search for the desired structure that we are working in, and we can bring it in quantum ATK directly. Apart from this, even if we need to bring the particular form file, so there are multiple support options. So if we need to have if we have VAS file that can be bring in, if we have a espresso file that can be bring in, CIF XYZ card, there are multiple import formats that we are supported. So any file you have, we can bring it in Quantumatic and start building the structure right from the nano level. Then what we have is we have different sets of nanotube builder. For example, if I need to develop a new material with a silicon germanium nanotube, so I can set up the particular element. We can set up the minimum number of atoms that we are requiring in the nanotube. We can also select concentric nanotube. So what we need to do is we can just select over here, and here in this way, three concentric nanotubes can be created. Once a structure is selected, we can build it up in. And if we need to basically increase the size of the following structure, so what we can do is we have a whole panel. So there are multiple tools that we can use. Once we need to do the particular operation like increasing the particular size dimensions, what operation that we would be selecting is we would be going into bulk tools. We would be selecting the repeat operation and the particular inserting in the value units by which we need to increase out the structure. So any complex structure that we are trying to develop can be built in a couple of seconds. We can just select out the particular values, we can swap the particular accesses, and there are multiple other options that we are having. For example, if we would be simulating it through a plane wave basis approach, although it's not recommended, but what I was trying to say with the vacuum spacing is there is some empty space. So that too would also be considered for atomic interactions that we would be trying to simulate. So to reduce that out, what we can do is we can go to the fit cell, clicking on apply, and it has reduced out the vacuum spacing to the least value that we can have. So even if we are developing out complex structure, we can directly build in. If we need to do further modifications like removing certain element in certain shape type. So for example, what we can do is we will be selecting this particular selection type. We would be selecting the area, and when we will press delete, so it will create a empty spacing. So in this, we can either do any sort of absorption properties calculation, because we would be having a surface site over which we can deposit different sets of atoms. We also have options of doping different sets of material to create different sets of and different types of material. So what we can do is we would be going in the fractional occupancy, and we will be basically changing whatever structure type that we are having. So going over here, we also have an option of generic alloy. So we can just set in the particular elements that are required, then setting up the repetitions, and we will be just able to create the following sets of structure. Apart from that, if we need to do any sort of interface creation, so multiple structures can be imported in. For example, I'll be just importing three different sets of structure. I can fix any one such point, and when we will be recalculating, so multiple complex interfaces can be directly built in. And here you have a particular mean absolute strain versus number of atoms graph. So whichever value is nearer to the particular x-axis, that is the origin position that we are having, will have the least amount of strain. That can also be seen what's the largest strain value and what's the average strain value that we are having corresponding to the structure. Once we are finalizing the structure, we just need to click on create. Now, as explained in the presentation, we have multiple ways of optimizing the structure. The easiest way is to use a quick optimizer. So we just need to write opti, and then we can select a potential that we are having. We can select number of steps. For example, 200 steps would be more than sufficient to optimize this set of structure. It will take around 10 seconds of time to optimize the structure. Once it is done, it will also set in our maximum force component value, and by which it has done the following changes. So this is how we start up with the following structure. Apart from this, in the builder itself, we have multiple other tools like an amorphous pre-builder. So we directly set out of some formula, setting out density, and we can directly build up entire structure. Similarly, we have a nuclear alloy builder. We can set out different sets of elements, and the structure can be built in. Apart from that, isocoherent builder to develop a complex material can be used. We can set out the order length, and once it is done, we can select and create the following structure. Similarly is the nanowire option that we are having. So we can preview the nanowire that we are having. We can select out the element for which the nanowire needs to be created. For example, uh, we need to have a particular simple cubic center cell. So in this way, it is a simple cubic structure that we are having. We can select the wire direction, and a quick nanowire can be created out of the same. So we can develop any sort of structure, materials, or devices out of it. Apart from that, even if we need to do NEB calculation, energy elastic moment calculation, we can import in multiple sets of structures. So we can have an initial point and the final point for which we need to do the particular set of NEB calculation. And then it would automatically interpolate the image and produce out the number of images that we are requiring. So for example, if we require 5 images, so we can set out the particular image count in the image constraints and then according to the different sets of simulation. Now, apart from that, even if we are developing complex materials like for MRAM interfaces, so that too can be done. We can select out the material type and the crystal type. Once it is done, it will generate out the entire structure and we can get the following structure, bring it to create. Now the next part is, this is the build part that we are having since we have limited time to cover out this following part. I shall be moving on to the next part that we have. Once a particular structure has been created in and we are satisfied with whatever structural lattice information that we are having, we just need to select over here, clicking on our workflow builder, and we will be getting a complete template from which the following blocks can be used. For example, selecting our LCO calculator. This being a metal extruder, so I'll just click on metal and it will set up the properties automatically. So these are certain templates that we are having pre-existentially that can be used and that can be manipulated. So any value that we are selecting in, we can change out the value and the particular structure calculations can be started. So the basic approach is to select out a calculator. Then as mentioned, we have different sets of blocks. So in the analysis, we have the particular band structure calculation, we have the current density calculation, we have the Coulomb density of states. So multiple parts can be selected in. For example, I'll just take a basic example band structure that produces very fast. So we can select it up here. Apart from that, if we need to do optimization, so we also have an active learning block that uses a GPU accelerated AI based auto generation of for molecular dynamics, which can be anytime used and can be simulated. So there are multiple tools that we are having to do the support analysis of any simulation task that is required. Apart from that, to generate out any sort of new MTP file, that is moment tensor potential file for certain new structures, we can create it over active learning simulation block. Once this particular part is done, we have selected out a calculator, we have selected out a property. What we need to do is we need to click on job as a script. Once a job as a script has been created, we just need to click on OK, save the particular file. And since we have an MPI process simulation, so we can set out the number of processes that is required. I'll set it 4. So for the Linux-based systems, we have this enable GPU acceleration, so we can enable the particular simulation task on the different number of GPU cores. Once the job is selected, the simulation has been started. We just need to click on the particular run the following simulation icon. Once it is done, so a live log file would be generated for us, and it would show us different sets of steps that are required for the process in the process to be completed. Once the particular steps have been created in, we can select out the different sets of files and the particular solution can be performed. So we can see we have selected the different 4 sets of processes over 2 threads that was automatically selected in, and the simulation has been started. So this way we can do and start up the simulation process, and it may take around 10 to 15 minutes for the simulation to be completed. Once such simulation is completed, we go to this data view section. I'll show an example of Morphos HFO2 because it has a molecular dynamics block and how the different sets of molecular dynamics simulation may be working. So here, once the simulation has been conducted in, we can check how the particular temperature changes the structure with the period of time, how the energy is changing the structure value. Then we can select out different parameters for which we need to do the particular sets of simulation tasks. And a movie file can also be exported in whichever is required. So we can select out the PS and then we can directly save the particular file as a MKB file or the MP4 file, whichever is required. So this way, any simulation result that we are obtaining, we can check. And once the optimization is done, how the optimized structure would look like can also be seen from here. Apart from that, we also have different sets of for devices. So in devices, we can have different sets of simulations to be conducted in, like starting up with the transmission spectrum block, and then we have the spectral current transmission, spectral conductance, and even this once the simulation has been conducted, after that also we can change out the
So your mic
particular.
is disconnected.
Hello, I'm audible. Hello, I'm audible.
Now it's fine, sir.
Sure. So these are different properties that can be calculated even for the devices. So this is a general overview. Quantomatic is quite large software to be covered in a single hour session. So this is how we basically access the software, how we go across different sets of simulation tools that we are having. And we have an open source library for learning the software. So we have this Quantomatic manual that is available over the web. So anyone can access the particular file. And now to start up with, for example, if someone is working only on the molecular dynamics part, so what he or she can do is he can just type in molecular, and we can just search in the following block how to use the following block, how a script looks like. We can check it over here, and we can also download the particular Python file that can be directly simulated in. So we can also download any particular Python file that can be started for the simulation. Whatever job that we are performing, all gets recorded as a Python file that can be anytime loaded. So whatever simulation that we are performing, we can anytime see in the editor section. And any changes that we are requiring, we can do it directly through the script also. Whatever cell that has been selected in, what are different sets of calculators, different sets of properties that needs to be simulated, all gets recorded in this particular Python file that can be edited. So it's a similar file that we can do and we can basically learn the software from. So it's a general overview of the tool and how basically JPU acceleration is accelerating different sets of functional materials simulation. Now, coming up to the other part, the different software that we are having. So, not to confuse a bit, so Quantomatic is different sets of software that is specifically designed for simulation of the particular materials at nano level. And Simpleware is focused on the reverse engineering part, the particular medical image processing or the material image processing. So, in this now the session, I shall be shifting up to the synopsis Simpleware software. I'll just give a brief presentation followed by the live demonstration as done for Quantomatic. So, just give me a sec. I'm connecting to the system. Yeah, so sorry for the wait. So, to start up with Simpleware, basically to introduce about the software range that we have in Simpleware, what it exactly offers is any data set file, image data set file that we are having, right? Either being the JPG image, the PNG image, the TIFF image. If we have multiple stacks of images, for example, if we have 20 similar images stacked one over the other to reveal the internal structure, we can what we can do is we can do a particular reverse engineering of the particular following part, and once the particular reverse engineering part has been completed, we can basically start up doing the any sort of reverse engineering parts like do additive manufacturing, whatever uh, part that we have reverse engineered for, we can export it as a STL file, we can export it as a CAD file, both supported for step IGS format. So there are multiple extensions that we provide. Apart from that, even if we need to export out a file for VR ML to do the particular visualizations, that can be done. And not just that, if we need to do a finite element modeling, computational fluid dynamics modeling, that too can be selected in. So whatever image that we are working, if we are working on a medical image, so we might be working on DICOM image dataset comprising of CT datasets, micro CT datasets, MRI datasets. If we are working on DICOM image for non-destructive resolutions, that too can be imported in. Then we have different sets of 3D image formats, STR, HPM, Analyze, Interfile. So multiple image formats are being supported that can be directly converted into high quality export models and also be used for 3D printing applications. Now, coming up with the part of Simpleware, how Simpleware is catering the life sciences and clinical application part. Starting up with the orthopedics, so we have the segmentation algorithm which uses automated segmented algorithms for any set of orthopedic data set that we are working in. We have three modes of approach while we are dealing up with simpleware. The first one being the manual based approach, in which we select a threshold range. We do start up the segmentation. We paint the region one by one for any n number of slices that we are working on. The next part is the semi-automated segmentation. What we have in the semi-automated segmentation is we select out a particular threshold window range. So whatever window range has been selected in, that will be easily be modeled in. And in the semi-automated segmentation that we have in Simpleware, we also have certain presets, like different presets for bone. We have different presets for uh, muscles, skin. So different regions are predefined that can be anytime used, and in a single click option, different parts can be segmented out. Then comes the particular product design analysis. Since we are working on patient specific image data set, so what we can do is we can do the customized designing of any implant parts, and even any processes can be designed in that can be later on integrated with the image data set. So we can check the surface division, we can also check any sort of error that is being conducted. We can do the finite element modeling and later on check the particular wear and tear over a period of time that any implant or a prosthetics may fail for. So what it does is it can directly cater us the need to design the product according to any specific patient. And I think many of you may know that every anatomy is different. So there is no way the generic implants would work for each and every patient because someone have different torso lengths. So if different sets of implants are being means same implant is being positioned in multiple patients data sets. So what it would do is it would ultimately cause trouble for the patient. It would cause the wear and tear of the following parts that we are basically dealing up with. Even if it being a titanium implant, it may cause irritation to the particular patient or may also cause wear and tear over a period of time around 7 to 8 years. What is the other way method is we have a existing design of any implant parts that can be modified in and it can be positioned in with the data set of the patient and all the particular inputs that we are having we can export it as STL files as a single printable object. So virtual surgical planning can also be conducted in pre-surgical planning and post-surgical planning all gets completed in the following section. Then we have the physiological flows. When we are dealing with any soft tissue data set, the most important part is we need to have the accurate mapping of whatever image data set that we are working on. And one such important application that is required is to have accurate physiological flows calculation. So in simple way, what we have is we have multiplanar reconstruction. So whenever we are doing the 3D image processing, We can basically develop out different planes, and we can set it along the any n number of surfaces that we are having. So we can have the MPR visualization, and ultimately we can set out the inlet points, outlet points. We can set out the contact points, node sets, and machine can be defined then for any specific region. And any sort of CFD simulations, FE simulations can be furthermore conducted in. Next step is the EM and neuromodulation. So one more options that we support in Simpleware is we can directly create the export file as the .hvm file that can be used for simulation. We can plant in any electrode data of on the following data set, and the particular simulation can be start to be performed in. Then we have it for medical device research and development. So as explained in the point number second, we have a good tool to directly integrate the particular any sort of implant device that we are having, or any other sort of medical device with directly doing its integration over any MRI data set, over CT data set. And not just that, even if we need to map out a CT over an MRI of the same patient, so that too can be done using the registration tool that we have. Last but not the least is the 3D printing preparation. So we have a dedicated module in which we can create high quality STL files that are ready for doing the particular 3D printing. And we can also modify the following structure. We can fix the surfaces if there are any sort of feature edges that are missing. So that too can be corrected out. And we can also do the color proofing of the same. So anytime the particular file can be checked, the particular wall thickness can be checked in, and the surface correction can be performed in. Next up is the features that are basically available in the latest version. So we have certain new features that have been included, like AI-enabled bone fill filter. So what it does is, earlier the solidification of any orthopedics part would be a tedious task. We need to use tools like a region growing tool. We need to use a tool like mass flood fill, smart paint to slowly cover out different parts and different regions that are present in any specific region of interest that we're working on. Now, what we have is we have a single click operation named as AI enabled bone fill filter. Whenever we would be clicking the operation, it will identify the nearby grayscale value intelligently and automatically fill up the particular bone part that is required. Then we have the spine CT automated segmentation that would segment out the spine data set into vertebra and sacrum. And furthermore, we can split up in lumbar spine, thoracic spine, cervical spine, whichever part that we are basically focusing on. Next up is the hip revision CT auto segmentation. So what we have is, if post surgery the particular patient needs any sort of the surgical planning. So what we can do is we can import in the patient data set that also has implant within it, and that too can be automatically segmented out. So for example, if the particular patient has a proximal femur implant positioned within the CT data set, so the software will automatically identify different regions like left femur, right femur, left hip, right hip, sacrum, and even the particular implant parts that we are having, and it will automatically segment out the data set for us. Not just that, it can also segregate out the cancellous bone and different parts that are subdivided in the orthopedic structure. So we can have the most accurate results in the least computational time. I will be further showing how the automated segmentation will be working in Simpleware. Then we have the mass similarity calculator. Since we are much more relying now on the AI-based segmentation methods, the auto segmentation method, so there needs to be a tool to check out the accuracy of whatever parts that we are segmenting in. To cover that part out, we have this mass similarity calculator that works on the principle of dice score. So whatever images that we are bringing, we have done the particular 3D reconstruction. We can overlap it with the auto-segmented part that we are having, and thus a dice score would be present with us, which should be having a range between 0 to 1, wherein 0 represents the particular mask are at all different, and 1 representing the particular mask being identical. So what a value around 0.95 or above would be treated as a group value for having a highly accurate segmented model. Next, we have the cutting guide tool, design tool integration. So even any cutting guide needs to be designed in any surface that needs to be designed. That can be done in simple way. We can also set in the pencil holes. We can set out the K-wire mapping. We can set out piece components. And ultimately, whichever surface that we are creating out, we can do the export of the same. Next up, Yeah. So now we shall be starting with the uh, different parts that we are having in simple way. So the base that we have is the scan IP that comprises of the image processing part. It has three sub-process. So it has a pre-processing part, it has a processing part, and then it has a post-processing part. In the pre-processing, we can crop the region, we can resample the region, we can rescale the region, we can do the alignment of the image data set that we are having. We can, if we are working with a 4D image data set, so that too is supported in simple way. We can also map the data set along all the particular time frames that we are working on. Then we go on to the processing part. In the processing part, we identify different regions. So whenever we will be obtaining a medical CT dataset, for example, as shown in this following sample. So we will be getting three views: coronal, sagittal, and axial. And in different views, apart from these three different views, coronal, sagittal, axial, the 2D views that we are having, we would be also getting a volume rendering of the same dataset that we need to work on. It's not a model yet, it would be just a volume rendering before the segmentation has been started. So what's the part of processing is, we would be able to segment out different regions present in a particular structure. Once the different regions have been selected out, we can do the particular modeling because, for example, we are only considering the cerebrum to be modeled to do the simulation for either the FE simulation if we are requiring it. So we can segment the particular part out, and once the segmentation has been done, we can select out the region of interest that we are requiring, and we can do the specific finite element analysis for the same. Similarly, if a particular patient has an acetabular cap implant to be positioned in along the pelvis, so what he can do is we can bring in the surface file, the STL file, we can position it with the image data set, and then it can be mapped out as a single object. So that would be covered in the upcoming slides. Before that, these are the important export formats. So we have all the particular image modalities to be supported in inside simple where we have DICOM image, interfine, analyze, any 2D images, text, BMP, JPG, PNG, TIFF, all are being supported. And once the importing has been done, we have done the processing. Next up comes the particular post-processing part. So post-processing involves smoothing of any surface that we are having, remove out any sort of noises, that noise removal filters, the 3D editing tools, morphological tools that we would be using. So there are multiple post-processing operations that we can use to further refine the data set that we are working. Once the particular refinement and all is done, we can export the particular file either being STL file, then initial graphic exchange file, SS file, ANSYS surface, Abacus, point cloud, MATLAB, VTK. So there are multiple export formats that are being supported. Next up is the particular finite element model. So the particular finite element model is simple. The comprises of two sets of modeling: finite element modeling as well as the computational fluid dynamics modeling. So here we can do the high quality FE models creation. We can also set in the material properties of on the basis of Young's modulus and Poisson's ratio. We can define the different sets of regions. So for example, if we need to have a higher meshing for this particular specific part, so what we can do is we can define the following region, and the particular once the particular meshing has been completed, we would be getting a much more defined mesh for the specific region that has been highlighted out. Once that is done, we have furthermore various export formats for the finite element model. Apart from that, we have an option of selecting the material type as mix of element type as hexahedral, tetrahedral, mix of hexahedral and tetrahedral, different sets of material properties, node sets, contact surfaces. This can be modeled in. Once these all have been completed, we can export the file type as abacus, we can export it as census file, COMSOL, Elestina, Nestron pattern, BTK, MATLAB. So these are multiple export formats that are being supported. Next up is NURB. So we also do support non-uniform rational B-spline structure modeling. So high quality IGS and stuff file can be created. So the different sets of files can be created, and we also have an automated patch fixing. So if we are working on complex structure size, so we can select out the region and we can apply the automated patch fixing. So high quality step files can be, or step or IGS files can be exported out. Then we have the CAD module. So any STL files, then any files from SolidWorks can be imported in SLD part, SLD SM file can be imported in. and can be positioned in with the software. So why I have highlighted out the SLD part, SLD SM5, because we also have a designing tool. What it does is it links SolidWorks software with simpleware. So whatever modifications we would be making in one software would get reflected in the other one. So any file that we are creating in, we can do live modifications and interaction with the patient image dataset that we are working on. So this is the designing module. How it works is, I'll just probably zoom in. Yeah. So what we have over here is we can select out different objects. So it has the curve, the liner region, the stem of the implant, proximal femur implant that is being positioned in. It can be selected, it can be applied in any sort of dimensional changes can be directly written. And once the particular surfaces have been aligned in, either we can do the particular FE modeling or we can export it as a single 3D printable file. We have different sets of Boolean operation in which we can combine different sets of structure. We can also check out any surface deviation or corresponding to a specific point. Apart from that, we have an option of internal lattice structure. So different sets of unit lattices can be selected and we can select the previous site and then the particular structure can be furthermore exported out. And then comes the automated segmented part that we are having. So in the automated segmented solutions that we are offering, we have the proprietary tools like AS Auto and TS Cardio, which has proprietary synopsis sampleware algorithms that are used to segment out anatomy. So we have current support for hip CT, ankle CT, knee MRI, CMF CT, spine, shoulder, and hip revision CT. For cardiovascular dataset, we have for heart CT as well as we can conduct heart valve analysis. We can select out the boards, the aortic arch, and different sets of simulations can be performed. But the latest inclusion has been the external models inclusion. So even if we are using algorithms like a total segmenter from 3D Slicer or Monai based model from NVIDIA, so now the particular following algorithms can also be used and we can furthermore use it for doing different sets of segmentation directly. Why it is helpful is because we can use different sets of algorithms to identify different tumor regions. And once the different parts have been identified, we can furthermore use the post-processing operations like refinement, the smart paint tool to further on increase any sort of small defect if any present. So this is how the particular automated segmentation module works. So this is one such example of a EMRI that we are having. It has automatically highlighted our different structure, the patella, fibula, femur, different parts have been identified. Apart from that, you can see there are certain landmark points. So these are key landmark points that software automatically identifies and creates for us. Once these landmark points we are having, we can use different types of measurement tool like point-to-point measurement or even the angle measurement to calculate out the distance for the same. Then we have it for ortho. So this is one such GIF-based video that we have, how the particular segmentation algorithm works. So the auto segmentation for this pelvicity took around 1 minute 40 seconds to complete. And once the segmentation was completed in, we had different sets of structures. So we have the particular left hip, we had the right hip, we have the left femur, we have the right femur. Also, we had the second part. Once the segmentation has been completed, we need to click on this generate a fast preview to basically help the software retain different structure that has been segmented out. That I'll further show in the upcoming live demonstration. So here we have the simulation time difference. So even for an expert user, if he is working, for example, on knee MRI, so it may took around 30 to 40 minutes to segment out the anatomy, but the same task automatically gets completed within 2 minutes. Although there might be a question, what's the accuracy of the segmented models that we are having since it's a disease data set that we are working. So it depends on two major aspects. The first one being the data set quality that we are operating on and the sort of disease that we are having. If it's patent on that particular specific disease, it will automatically segment out the part. But even does full task for us, it will basically ease out. So it will do 80% of segmentation, and then we can do particular 20% segmentation by using semi-automatic segmentation algorithm, and further on use refinement tools to refine out different sets of regions. So this way it helps in faster generation of models. Similar is one such example of soft tissue. So specifically cardiovascular data sets are very difficult to model out because they have multiple structures present within it, and to identify each and every region it's quite difficult. So what we can do is we can use it as a landmarking tool. We can apply the auto segmented algorithm, and it will identify the different regions that are being present, and this is one such GIF that can be directly exported out. Apart from that, even if we need to do the reslicing, so we can cut the structure in half. For example, to visualize a VST defect, that is ventricular septal defect, we can do the segmentation within the software. And furthermore, once the segmentation has been completed in, we can check out the internal structure to check out the defect. So any sort of pre-surgical planning can be performed there. We do have one such video of the same. So this segmentation was performed by me. This is our patient's data set from AIM study, wherein what we had done is we had created a 3D printed model of the following patient data set. The following patient had VSD along with TORB. So the model was created. It's a four-section model that was 3D printed out. It has magnetic connectors also. So different structures can be seen over here. We can basically disconnect different sets of structure. I'll just fast forward the video. Yeah, so this way different sets of structures can be identified in, and the internal surface can be easily visualized. Once the internal surface has been visualized, we can select the defect. So this is the particular point of VST defect that is being shown in the following video. So it's a four-sectional model, so different four sections are present that can be easily removed and then bring back together. So this is one such way to work on the pre-surgical planning apart from the VR-based approach. So what's the VR-based approach is, we have done the same set of segmentation. Uh, we just leave the particular 3D printing part out, and whatever output that we are generating, we directly visualize in a VR headset. So that is another option to reduce the need on additive manufacturing. So that can be used as the other way approach. But to have a particular haptic feel, we might still need to be using this sort of models to check the accurate structure dimensions and to check it more clearly. Then these are some of the system requirements that we require to run the software efficiently. We require, currently the software is supported on Windows systems as well as Linux. Then we require a minimum of 16 GB or higher of RAM. Then we require a CUDA enabled graphics card. So these are the basic requirements for the software to be run. I shall be now directly switching on to the live demonstration since we have very limited time. I'm just sharing my screen.
That used in DFT like GGA, DFT plus E, or is there it is GW approximation methods?
Ma'am, both are available. So we have the DFT plus GGA as well as GW approximation. So both are being supported.
Sir, here you particularly mentioned that green function method. You are
Yes,
preferring
ma'am.
as a GW approximation or any other functional?
Ma'am, we have user-defined function for that. So we have multiple options. So the NGF that I was mentioning, we have user-defined functions that we can use. We also have the GW approximation that can be used in. So there are multiple approaches that we can select.
Sir, like this, we are having many softwares like WASP, Yabo, like
Yes.
Quantum Espresso. Why particularly this? Why it is better than those softwares?
So what advantage that we have in quantum ATK is we can integrate the VASP file also, we can integrate the espresso file also, and we can, whatever simulations that we are performing, we can have a GPU accelerated simulation for the same. So if the simulation time is, for example, 3 days, 4 days. So it gets reduced down to around 15 hours, 16 hours using the GPU accelerated simulation.
So only the computational cost is the reason for choosing this software. Is there any other advantage for
Accuracy
using?
is also quite good, ma'am. And then we have integration of all the software tools that are available. So it's a complete bundle package that we have. So even if someone's working in the materials field can use it, even someone working in device field can use it. So multiple users can working on different domains can use the software for their respective purposes.
Yeah, okay, sir. Thank you.
Yeah. So shall I start with the simple way down? After that, I shall be covering out any doubts that we are having for both the software. Yeah, so to start up with the software, let me just switch on camera. Yeah, so to start up with the segmentation software that we have, so whenever we will be importing the image dataset over the left-hand section, we will be getting the image information, the physical extent of the images, the spacing between the image dataset that we are working, the total number of object counts if we have imported any STL or CAD files. To import in any file, we have multiple image import formats. We have the DICOM images, wherein we can select out the DICOM folder. Then we have the DICOM images for non-destructive evaluation. We can also have the PAC server connectivity to directly connect with the hospital server. Then we have a stack of raw images support. We have the 3D image formats. We have a STL CAD file. So there are multiple formats in which we can import out the file. If we are working on certain existing project, we can anytime open the following project and basically it gets recorded as a SIP file, that is scan IP project file, or you can say simple web project file that we are having. So if there are multiple users of simple web, they can interchange the SIP file. It is all back compatible. So even if the segmentation is done in the future versions, it can be brought down in the lower versions too. So this is one such advantage that we have. Apart from that, we have a dedicated helpline support section. So I'll be just closing automatic also. Yeah. So it's a dedicated tutorial guide that we have. So right from starting the basics of segmentation from CT, proximal tumor, how we are doing that. So it's a step-by-step guide how we can access the sample data set that comes along with the software boundaries. We can anytime go and check it, what's the algorithm that is being used, how different tools are used to basically visualize the data set more clearly. So we can set out the volume rendering also, then how to use the resampling tool, how to use the rescaling tool. So there are all the particular tools that are available are mentioned in very detailed and interactive way for the simple way tutorial. Yeah. So to start up with, I'll be just taking the example of pelvis as it's very easy to explain out to show the segmented algorithm parts. So we have taken an example of pelvis, the CT dataset that has 280 slices of 279 slices of image dataset in the following data. Once it is done, all the particular sets of DICOM data text information gets recorded over here. We can anonymize the particular DICOM data text and then we can click on the finish. Once the data set has been loaded in, we can get different sets of views, the coronal view, the striatal view, the axial view. And this is the particular volume rendering. So it's not a model yet. It's just a volume rendering of whatever stack of images that you are working with. You can see whenever we will do any sort of image processing, 3D image reconstruction, there would be certain noises, either metal artifacts or nearby noises that are being captured during the scanning part. To remove out such noises directly, what we have is we have certain operating procedure. So we can use a recursive Gaussian filter, which is recommended for medical use between a value between 1 to 3. Between 1 to 3, we can select and we can just type in the file. For example, selecting 1. We have selected the cubic and isotopic value, so it will select the following value in all the three views, and we can see the majority of noises gets removed in a single click operation. So this is one such way to remove out any noises, the larger noises that are being present in the dataset. Now comes the particular segmented, how to have the segmentation started. Since this resampling operations, what it does is it can upsample the following dataset as it will basically reduce out the spacing between the images and furthermore increase the number of images that are pre-existential in the dataset. So if I'll be just typing the value 0.34, 0.34, so it will be just multiplying the dataset by 2, but it will also increase the memory computation requirement. So currently it's around 70 MB. Once I will click on apply, it would be somewhere around uh, 700, 800 MB. So it's around 726 MB of data sets. What it has done is earlier it used to have 278 slices. Now it is 558 slices in the actual view. Similarly, the number of slices have been increased in the current view. So that earlier. Now we have much more accurate mapping of data sets. So we can anytime resample, that is upsample the data set. If we are doing the characteristic of, for example, a porous aluminum material, so since it's also used in material image processing, we can also downsample the following dataset. Once the downsampling is done, we can basically work on larger dataset that has datasets in all the way to around 10 GBs, 20 GBs of dataset can also be simulated. To start up this segmentation, I'll be just showing the semi-automated segmentation and the fully automated segmentation as we have limited time to complete our session. So we can anytime select a bone preset, selecting a value a little bit lesser. To start up the segmentation, we can click on fill cavity resulting one and only keep the largest resulting agent. Once we do that, we can just click on apply and it will start doing the segmentation for us. What it will do is it will create a pool model for us in which it will be having all the particular sets of different structures that are comprised in HIP as a single structured model. Also, we have clicked on this only keep the largest resulting island. So all the small disconnected islands that we are having will get removed. Since this was the volume rendering of the dataset that we were working on, once the segmentation has been completed and the mask has been produced, uh, in this case being mask 1, we need to click on this generate a fast preview and we can easily check out the single segmented mask that we have obtained. Now there are multiple operations that we can perform. First one is we can solidify and fill all the particular gaps that are being present in dataset. But wait, what if we only require the particular right hip part, and this is the much more focused area that we need to work on. So to cover out that application, we have a split region operation. Here we have certain presets. So we can use a hip operation and here we can mark out different regions. So we have two methods to mark regions. Either we can select out the value in 2D view, we can just select out the particular hip left, then hip right. So we will be selecting the outer boundary and it will be starting the marking over the way. But we have a better approach. What we can do instead is we can toggle on this live 3D preview and then we can start marking directly in the 3D view. So this way the particular line can be observed and we have marked in the particular over here. So what we need to do is we need to just mark around the boundary conditions. So once the particular boundary conditions have been marked in, I'll be selecting the same for hip right. And similarly, we would be marking one over out here. Similarly, femur left. So it's a rough marking that I'm currently doing. If it requires around 2 to 3 minutes to properly mark out different regions that have been present. Once it is done, I'll also mark out the sacrum region. Once these all parts are faded out, what we will do is we can either select a preview to check how the different segmented regions would look like. And if the result is getting satisfied, so we can just click on apply and we can furthermore produce out the following part. So it takes around 30 seconds to generate out a fast preview of the same. It also depends on the GPU as well as the RAM of the system that we are working on. So it will start and take around 20 more seconds to complete out the entire process. Or even if we are satisfied with our marking, so we need not to also review the preview in certain cases. So this is the particular manual based or semi-automated based approach that we are showcasing. Just after this, I will be showcasing a auto segmented method how we can basically highlight out different regions that are being presented. So once it is done, why we have done the particular splitting is, for example, if we need to position out an SW cabin plant. So the next step that we would be doing is we would be going in a surface tools option. We would be bringing the particular STL file, and once the STL file has been brought in, we will be doing the registration over the existing dataset. I'll just cancel out this process, clicking on apply to directly generate out different structures. So it will take another 5 to 10 seconds more to furthermore split up. Once the particular splitting and all is finished, uh, we will be using a smoothing filter and a bone filling filter to fill out all the particular cavities that are present in the polling part. And once that is done, we can bring out the particular surface structure. Apart from that, the auto segmentation block that we are having, we have an AS ortho for hip revision CT that we can use in this polling case, and it will automatically highlight different regions and do the segmentation for us. Once this all part has been done, what we can do is we can have a model option. So we have four types of model to be created in. The first one is the surface model, the second one being the FE model, the third one being the nose model, and the fourth one being the CFD model. So it has created different regions. Now, for example, if our working area is particular hip right, so we will be just highlighting out the hip right region, and we would be isolating and working on it. So once the particular fast preview is generated, we will have a better clear picture of whatever segmented region that we have produced. Now, for example, if our region was right, I can just isolate this part out, and now I can start working over it. So to fill up all the particular gaps and all, I'll be just clicking on a bone filling, and it will automatically solidify the following region for us. The bone filling operation takes around 2 to 3 minutes to fill up the entire bone. Meanwhile, what we have is I'll also show for the same dataset how an auto-segmented algorithm works. Meanwhile, this particular file is being loaded. So whatever task that we have done till now, all now let's it's all using a auto-segmented algorithm in simple way. We can anytime select on the dataset, and then we can basically produce out a 3D printable model or even the FE model that is being required. So I'll be just opening the particular file, same file that we were working, I'll just type up. And to start up with auto segmentation, I'll be selecting a hip region city. So both this task takes around 2 to 3 minutes to the particular segmentation completed. So it would complete in the background. Meanwhile, this is the particular output region that we have generated after segmenting out different parts. I'll be just generating a first preview. So you can see the particular gaps and cavities that were present were now filled up. Now to bring in any surface file, you can click on import surface and any STL and CAT files can be brought in. So I'll be selecting the data. In this, I have an STL cabin plant STL file. Whenever we would be importing surface, we can check whether the file is watertight or not, any self intersections are present, bad orientation is present. And if there are any sort of errors, we can directly fix it up using a single click operation like fix. Once we have brought in the data set, we need to click on zero position to bring it at the origin position. And then we can furthermore to the ultimate positioning to shift it up. We can go into position and orientation and we can directly shift it to the exact requirement point. You can just select it and then you can rotate on the axis that is required. Yeah. So like this, our positioning can be done and we can easily model the particular part out. So once it is done, we need to generate out a surface model. I'll be clicking on models, surface model. And over here, I can select out different types. So for example, if we require an STL for 3D printing, we can select it up and then we can start building the model. Once it is done, I'll be also requiring to generate the same for the hip right that we have selected in. So for this hip right, what we need to do is we need to convert it into a surface first. So we have dataset conversion from mass to surface. Select out the file. And once the particular surface has been rendered, so we will be getting a different surface over here. And now both the surface that we are having can be brought in and can be exported as a single SQL file. We can also involve different sets of connectors, the node points, and different sets of additional points that are required. Meanwhile, in background, the auto segmentation has been completed. So whatever process that we had done, the manual segmentation, so the task gets a better output is generated using the automated segmentation for the same. So this is the segmented output that we have. And it basically eliminates the need of this particular tabs that we are having to a greater extent. Because even for some cases, we might be requiring the image processing tabs and additional operations for doing the further refinements. So this is a basic overview. Apart from this, we have different sets of models creation. So we have a finite element model tab in which we can set out volume meshing, we can set out the element types, we can set out material properties on the grayscale variables. So setting up Poisson ratio and Young's modulus. We can define different regions. We can set contact point shells, refinements, mesh refinement, and the export type that is required. So this is a general overview of the software for now. How we basically do the particular reverse engineering and create out the model, and then how we can export it for doing the 3D printing as well as the particular surface model for doing the simulations. So if anyone has any doubts till now, you can let me know either for quantum ATK or for simple bit so that we can cover out the same.
Hello, sir, are you done, sir?
Yes, sir. At my end, it's finished. If someone has any queries, they can let me.
Any doubts from?
I'm also sharing my contact if someone wants to contact after this session. So
Yes, sir.
these are my credentials, contact number. So you can contact me over here. My mail as well. My software. I'm also typing it in the chat box.
Yes, sir.
So thank
So
you,
good
organizing
afternoon,
team.
um, Ayush. This is Somshekhar from IT Dharwad. So can you hear me?
Yeah, good afternoon, sir. I can hear you.
Yeah, yeah. Sorry, I was not there beginning of your presentation. I mean, firstly, thank you for accepting for this talk, and then I think you might have actually liked your presentation. So I saw that a lot of demo that you're about the software. So I'm happy to see that. Thank you for a wonderful presentation. So I have one quick question. Do you have any demo or trial or student versions where students can actually explore this software, something like student version?
Yeah, we do have some evaluation version. So there's an evaluation site
Okay.
in which can register and basically access the software. So I am just sharing the evaluation link in the
Yeah.
chat box. So they can register, sir, whichever tool they like and explore the same. So we will be contacting accordingly. I have just typed in the chat.
Yeah. So maybe our we will also pass that information to all our participants. Um, any other questions from participants? Okay. So I think thank you, Aish, for your presentation, for your time, for joining us this wonderful talk, and thank you once again. So I think I vote to you, Prashant. Please.
Yeah, thank you very much, sir, for this
Yeah.
session.
Please visit IIT Dharwad sometime. So we will be happy
Sure, sir.
to host you. We can also invite you for some other events as well. But if you come around, Dharwad region, please, send me email or WhatsApp me. I'll be happy
Sure,
to meet you. Yeah.
sure, sir.
Thank you once
Thanks for
again.
the opportunity, sir.
Yeah.
Thank you.
Thank you. Bye.
Okay, thank you, sir. Thank you for your wonderful session for software. So we'll break